Welcome everyone. My pleasure to introduce Dongwook, who's visiting us from Duine. Came from Aachen via Helen this morning. Short trip. Dongwook got his PhD working with Young-Woo Lee in postdoc, and then moved to do the postdoc with Yuri Kruzov, and has actually turned out to be a long postdoc. And we're now starting September. Dongwook is moving back to Korea to take up a faculty position, to start a faculty position there. I think Dongwook is a very well known person in the field of orbitronics, which I think of orbitronics, optical effects in spintronics settings. I always think of Dongwook. I think it's one of the main drivers behind this field. So we're very excited to listen to your talk. Please go ahead.
Yeah, thanks, Rembert, for the invitation. For a very generous invitation. Introduction. Yeah, my name is Dongwook Go, and yeah, I'm very happy to see all of you. And I suppose you are from all very different backgrounds, but somewhere related to materials and condensed matter physics and chemistry. So what I'm going to tell you is the story in my research on orbitronics. And then this is really becoming an emerging field in condensed matter physics in many ways, which I'm going to introduce you later. So the field is somewhat similar to what people call orbital mechanics in astromechanics. For example, this is a picture that I've taken from the webpage of NASA for the mission Artemis 1. So the ideal mission was to launch a rocket from the Earth and send it to the moon. But instead of landing on the moon, they decided to orbit around, and then it came back to the Earth. So as you can see here, the orbiting motion of the spacecraft from the Earth is transferred to the moon, and it came back. So it turned out to be a success. And what we are trying to do is something very similar in nanoscale world inside of a material. And of course, in a material, we have an array of atoms here, and consider these atoms as planets, and electrons are circulating. So electrons are our spacecraft in this case, and you might wonder whether the motion of orbits inside a material is quite random, it's hard to control. But what I'm going to try to explain you later is that by applying electric field, you can induce a coherent motion of orbiting motions, and it can propagate in space, like this animation. So what we mean is that we generate an orbitally polarized state, such as px plus ipy state carrying finite angular momentum, and it's propagating into neighboring sites like this. So I will explain you key physical principles of generating orbital angular momentum and how we transport them and how useful they are and what we can use it for and how exciting these fields are. And towards the end of my talk, I will also mention some challenges and very unresolved and conflicting, but not too much. But today I'm going to mostly focus on things which we think we at least understand to a certain aspect. To start with, probably it would be very unintuitive for you, many of you, to think about orbital current or orbital angular momentum as a degree of freedom. Because if you think about electron, of course it has charge degree of freedom and also spin degree of freedom attached to a particle. And if you solve the Dirac equation, you get this spectrum of electron and positron get by 2 times mc squared. But you don't have orbital degree of freedom here. You have only charge degree of freedom, 1 in electron and 1 in positron, and spin degree of freedom on each sector. But in solid state, we have a lot more sub-splitting structures. This is the band structure that I've taken from my calculation. Or this is the iron. And you see that there are many bands. Actually, the number of bands when you calculate the band structure calculation is that the total number of bands is given by the product of the number of atoms in the unit cell, the number of orbitals, times the number of spins. So that's why you see a lot of bands. And many bands are in fact originating from the orbital degree of freedom of the atom, which makes solid. So in a sense, orbital degree of freedom really emerges in solid state, which is the information that doesn't exist for a free particle in vacuum. And orbital information can be in fact considered as an internal degree of freedom, like the spin degree of freedom. That's what I'm going to try to convey you. We can even control this information and transport. But people haven't studied much of orbital angular momentum in condensed matter physics and solid-state physics, because in crystals, a continuous rotation symmetry is broken because of the lattice structure. So it means that the operator R cross P is not a good quantum number because it doesn't commute with the Hamiltonian. So therefore, although we can think of all different type of orbitals, although these real orbitals carrying no angular momentum are more natural states adapted to the crystal symmetry, while if you think about these type of complex orbitals carrying finite orbital angular momentum, it's generally very much suppressed. An intuitive way to think that these orbitals carry finite angular momentum is that you see a donut shape here. So it means that electrons can actually circulate around. But if you look at these real orbitals, there are several nodes which hinders electrons circulating. So you can also intuitively understand the shape of these orbitals. But anyway, I told you that these complex orbitals are very much suppressed. And empirically, actually, if you look at spin moments and orbital moments in typical magnetic systems, iron, cobalt, and nickel, you see that the orbital magnetic moments are way more suppressed compared to spin magnetism by an order of magnitude. This is because for spin, there is spontaneous spin ordering, like exchange interaction. But for the orbital, it is indirectly induced on top of the spin ordering, only if there is a spin-orbit interaction. So therefore, a lot of works done in the past, especially since the 70s, were dealing with these real orbitals. So they are actually, I would call, classic orbitronics already back in 70s. And personally, I learned really a lot from a very nice textbook written by Daniel Konski, who unfortunately passed away last year. But I think this book is really a legacy from him. And the classic orbital physics dealt with mostly stabilities and phases of materials due to orbital degree of freedom. For example, it really started from Gutenberg-Kanamori rule. It roughly states that if the spin ordering is anti-ferro, then orbital ordering becomes ferro. But if orbital ordering is anti-ferro, then spin ordering can be ferromagnetic. So these orbital ordering and spin ordering, they go in the opposite sense. So it was already theoretically appeared in 1950s, but then it turned out that the orbital degree of freedom couples to the lattice distortion, cooperative flux, and there can be an instability toward distortion. And distortion comes together with orbital ordering of the orbital characters carrying no angular momentum, but these order can be stabilized together with the lattice distortion. And an elementary excitation attached to this ordering is called orbiton. It's a Goldstone boson of orbital ordering. And I think there are many experimental evidences on orbital ordering and orbiton as well. And also, already 20 years ago, there were a lot of studies, especially on manganese compounds, where spin ordering and orbital ordering are entangled together. And the reason is that if you have orbital ordering, for example, in this z-axis direction, then you have additional gain of the kinetic energy, and this promotes additional channel for the superexchange interaction. So the magnetic phase becomes more anti-parallel in this z-axis direction, and then it really kinetic anisotropy given by the orbital degree of freedom gives rise to different spin phases as well. But again, I want to emphasize that all these nice works done in the past dealt with orbital character, real orbitals carrying no angular momentum, because traditionally we have thought that orbital degree of freedom is orbital angular momentum is trans degree, which is quite small. But nonetheless, there are some theoretical predictions already from 2005. This is, as far as I know, this is the first paper which predicted generation of dissipation as orbital current, written by Bernevik, Hughes, and Zhang. And they show that electric field in pit of silicon can induce dissipation as orbital current in a similar fashion of the spin Hall effect. So what they have studied is basically this full band complex of silicon, and the Hamiltonian in this region is described by the simple Hamiltonian. This can be considered as zero spin-orbit coupling limit of the Luttinger Hamiltonian that people study a lot in gallium arsenide. And so in a sense, I think this model is understandable because it's analytically tractable, people can understand, and also orbital quenching, even if they are splitting, you see that from this Hamiltonian, L can still be considered as roughly quantum number. So L is not really completely quenched at all, as long as we stay near this high symmetry point. But a surprise was that actually when similar conclusion was made for transition metals in 2009, in a paper written by Fontani and Tanaka and their colleagues, they predicted that there is very large orbital Hall effect behind spin Hall effect and unmasked Hall effect. And they claim that orbital Hall effect is the origin of the spin Hall effect. From their calculation that they have shown that orbital Hall effect is about 10 times stronger than the spin Hall effect. And explain that if there is spin orbit coupling, then orbital Hall effect generates a little bit smaller spin Hall effect. But the main, I think, back then the criticism was that also when I studied my PhD was that how can we even intuitively think about orbital transport or orbital current? The main problem is that transport of orbital angular momentum is very different from charge transport or spin transport, which already exists in the ground state. But orbital angular momentum is a kind of quantity that is frozen in the ground state. So how do we even transport it if it's not there in the ground state? So what I'm trying to explain you in the next few slides is that orbital angular momentum is a bit like a ghost, which appears and disappears during the transport. So what I mean is that if you have a ghost, and if there is a perturbation like electric field, then orbital angular momentum is induced in non-equilibrium states like this. But then when the perturbation is off, then it disappears again. So but many things happen in this transient state, and this non-conserving nature of angular momentum is really the key property for understanding many orbitronic phenomena. Because orbital angular momentum is fundamentally not really conserved because it interacts with the lattice degree of freedom so strongly. So it cannot be treated as a perturbation anymore here. Yes?
Just a quick question.
Yeah.
Should I think of this ghost as just a virtual transition now, or is it actually something physical that appears but then disappears again?
Let's say this is an electronic excitation, single particle excitation in the ground state without perturbation, but this excitation doesn't carry angular momentum. It carries charge and the spin, but not orbital angular momentum. But if you apply E field, then this excitation can carry angular momentum. So it's still the same excitation before and after the perturbation.
You can measure, so it's not a virtual. So it's
Not a virtual.
Spin transition where it's the spin hopping, which is virtual.
Yeah.
It's actually something that you can measure in with the electric field.
Yeah, I think you can measure it.
And just because that distinction for me is quite important.
Yeah. I think what you're saying should be correct. Yeah. So today, as I said, I'm gonna rather stay on. I think most people at least agree because this is really the field that is rapidly evolving over time, and there's a lot of controversies. So I will stick to something like physical principle most of the time. So to start with, I'm gonna start with the electronic structure, that how the orbital information is encoded in the band structure. And then I'm gonna tell you the concept of orbital texture as schematically shown here. And then I'm gonna move on to study the effect that results from orbital texture in non-equilibrium, in the electric field or under current. I'm gonna explain you two mechanisms for generating orbital momentum. One, orbital Hall effect, and the second one, orbital Einstein effect. And third, I will explain you one example where orbital currents can be useful, especially when it interacts with magnetization. And I will show that this can be very helpful for controlling magnetization by electrical matter that people try to achieve in spintronics for many decades now. Okay, to start with, I think I have to define what I mean by orbital information. One disclaimer is that in this talk, I'm going to focus on mostly atomic orbital angular momentum, so-called Muffin-Tin contribution. Of course, you can also think about non-local orbitals throughout the boundary of the sample by itinerant motion of electrons. But in this talk, specifically, I focus on atomic orbitals, just for convenience of the discussion. So the potential profile that electron feels is like very dramatic, actually, if you look at the potential profile in real solid. So there's almost infinite potential drop near atomic core, but potential is really flat in the region. We call it interstitial region. So therefore, the solution in a solid state called block function looks a bit like this. In the interstitial region, the solution is really pretty much like plane wave. There's only very slight deviation of it. But inside of the muffin tin here, near atomic core, it looks really like atomic orbitals. And the wave function is smoothly connected at the boundary. Of course, they should be. So therefore, you can imagine that one orbital here in this muffin tin is connected to another atomic orbital here through interstitial plane wave. So it means that, for example, if you perturb an atomic orbital state here, because wave function is smoothly connected to other muffin tin, this information will transfer. So this is one way of imagining how orbital information can be transported over distance. And the orbital information is included in these U parts. I think in some cases people consider seriously, but I think this is the part that I think we didn't pay much attention so far. So to understand which information is included, let me have another approach by starting from atomic orbitals as basis function. So starting from atomic orbitals, more rigorously, this is called binary functions. And then we can have linear combination of these binary functions to construct a block-like function, which is an eigenfunction of the discrete translation. So this can serve as a basis function, and so that you can expand block function in terms of these block-like states made out of atomic orbitals. And this U is a coefficient, and this characterizes how much orbital character is in this block function. And generally, this U is a function of K. So therefore, you can think of variation of this U as a function of K. And this is what I mean by orbital texture, which I'm going to introduce you later. But anyway, by using the fact that the plane wave doesn't change much inside of the muffin tin, you come to this equation, meaning that U indeed contains the information of atomic orbital here in this phi, together with the character U. I intentionally wrote it as U because it's actually a gauge coming from the orbital degree freedom. So it's deeply related to the Berry phase physics eventually. So okay, this is the information that we are talking about. So then I want to talk about orbital character included in U. So an intuitive way to think about orbital texture is that first, let's think about one px band and one py band. This can be a two-dimensional system with px and py orbitals in nearest neighbor hopping, also second nearest neighbor hopping. But in the nearest neighbor hopping, only in the cubic lattice, px and py orbitals are completely independent. They don't mix each other unless you break the symmetry. But in general, there will be interaction between the two by higher order interactions, hoppings. So therefore, if we mix px band and py band, we have two bands. One is where orbitals are pointing in the direction out of the origin. I call this a radial band. And then the other band, which is inside, will have the orbital character like this. Let's call this a tangential band. It's quite intuitive name, right? And so this is nothing but what we call orbital texture. And this is indeed induced by orbital hybridization coming from the hybridization taking place at this crossing point. So whenever there is orbital hybridization, then you can have orbital texture. And this is quite universal actually in many multi-orbital systems. And generally, hybridization also depends on the symmetry of a crystal. But orbital texture can also exist in many crystals with very, very high symmetry, with all the mirror planes and inverter symmetry and time reverse symmetry. So this is the main difference compared to the spin texture, which you need to break symmetry to induce it. For example, in silicon, that I have shown you in previous slide from the paper of Bernevik, actually hole bands have radial and tangential textures. In fact, although it wasn't discussed much in this paper, but one can show that orbital characters are aligned in K-space like this, in two hole bands which are split. And orbital texture can also be found in many metallic systems. For example, in metallic titanium, FCC crystal, orbital character changes continuously from like Z square orbital, X square orbital to ZX character in this case. But in principle, there are many characters, and all the characters, they change rather smoothly due to hybridizations. And this is actually a very important feature that you find especially in metallic systems, because orbitals are really spread generally. So, and usually there are many channels that orbitals can mix somehow. And probably if you are doing theoretical physics, you might wonder what is the Hamiltonian of it, right? So the Hamiltonian, the minimal type of Hamiltonian you can think about to describe orbital texture is this type of Hamiltonian. So again, yeah, this is the one that I actually have shown you before, Oettinger Hamiltonian without spin-orbit interaction. So, and this L can be p orbital as well, but p orbital angular momentum case, you can write down a metric representation for Lx, Ly, and Lz in the following way. So diagonalizing this Hamiltonian is really simple quantum mechanics exercise by fixing the quantization axis along the direction of k. So then you get three different states depending on the quantum number m, and m equals 0 corresponds to radial orbital like this. So basically, orbital points like this along k direction. But for m equals plus minus 1, they form degenerate tangential space. So one looks like this in case ky plane, and the other one is pz orbital. I neglected pz orbital in this case because pz doesn't interact with in-plane orbitals, in particular for this. And if you look at the energy dispersion, energy levels are split in a quadratic sense, proportional to gamma k squared because of this one. So this is somewhat very similar to, for example, the Rashba model that you probably heard about, but it's different in the sense that you don't need to break any inverse symmetry or time reverse symmetry. And also the energy splitting is quadratic in K. So then let me move on to dynamics. What happens when we perturb the system in the presence of orbital texture? So if there is orbital texture, imagine that we start from this state here, pick up this state, and drop it here suddenly. So imagine, let's perform a thought experiment. We pick up state here at ky axis direction, and drop it here. And what you immediately see is that orbital here, px orbital, is no longer eigenstate. The true eigenstate is this one, or the other one. So therefore, there will be dynamics, because this state is no longer stationary. So mathematically, we can write down our initial states as a proportion of the true eigenstates at k plus delta k position with some coefficients, and the ratio will be determined by how much we shift these states. And as I have shown you, these radial and tangential bands have quadratic bands. So their energies are different, meaning that the evolution rates will be different. So over time, at the end, what we can show is that, in fact, there is a coupled oscillation between the orbital angular momentum Lz and the quadrupole moment, which is a symmetric product of Lx and Ly. So these coupled oscillations between this orbital quadrupole moment and dipole moment, it's in fact quite a general feature that you find often in many systems. And this is also one crucial difference compared to the spin dynamics, where spin dynamics remains spin. It's aerodynamics, SU2 dynamics, but the space that we are dealing with is actually bigger than SU2. So therefore, we have additional degree, which is a quadrupole moment in this case, p orbital systems. And one important lesson is that what I've shown you so far is that all these states that we studied from radium condension orbitals, they are all real orbitals, like px orbital or py orbital, and they don't carry any angular momentum. So, but in dynamic situation, orbital angular momentum can appear, but disappear at the same time. So, and this is irrespective of the orbital quenching in the ground state. So it means that in non-equilibrium in general, we can induce dynamics of orbital angular momentum, and we can even transport it. So in the steady state, in DC electric field, you can think of a perturbation given by DC electric field. And by DC electric field, you can think of coherence proposition induced electric field in this way. So it basically mixes radial and tangential bands, schematically shown here. So radial band will mix slightly with tangential band in this perturbative sense, and also tangential band will mix radial band like this, up to the linear order, linear perturbation theory. So, and then eventually for this particular model, one can show that induced orbital angular momentum will be proportional to k cross E, and also inversely proportional to the cube of the k. So it's in a way similar to Ampere's law, but in k space. So you wrap around in the axis of the electric field, and angular momentum is induced in this arrow. And important thing is that L is induced in the direction of E cross k. So finite OEM orbital angular momentum can be induced in the steady states. So this is, I think, a quite general conclusion that people can make even for central symmetric systems, even for really simple systems. But this mechanism also plays in more complicated materials. So starting
That's more interesting.
This is for me interesting.
Okay, no question. All right. Yeah. All right. Good. So I have explained you that now orbital angular momentum is induced in the direction of E cross k. So in this case, when I apply E field in the direction of x, then if you take a cross product with k, and you see that states with positive ky will have positive LV in the steady state, and states with negative ky will have negative LV in the steady state, which still exists in the ground state. But another thing that you notice is that states here and then below here, they are already moving in the ground state. So when you think about electronic system, it's important to notice that electrons are not just static in the ground state. It's just that there are all type of modes that are propagating all different directions. But it's all compensated in the sense that there is no net particle flux. So left movers and right movers, they are all compensated exactly the same number. But by applying E field, what we have just shown is that orbital angular momentum is induced depending on the direction of the motion of the electron. So this is the cause of the orbital Hall effect. So orbital Hall effect is it's driven by induced orbital angular momentum effect, but this is the current carried by the ground state current. So it means that there's no dissipation channel as long as this mechanism is involved. Of course, there is also dissipated channel because of orbit current like this. But the nature of orbital Hall effect is not really this photon picture, but it's really due to coherence proposition caused by external electric field. So I think this is really the important message that I want to convey on the first part. And if you have any question, please feel free to ask.
Can I ask
Yes.
question? This is very similar to the theory for the intrinsic spin Hall effect in the Rembert system, right?
Exactly.
Then we know that the spin relaxation is very important somehow, and it
Yes.
changes a lot.
Yes.
And so here I also assume that there's orbital relaxation processes that changes pictures somehow.
Yeah, that is a very good question. But actually, that question was exactly addressed by the paper of Bernadette et al.
Okay.
And they have shown that the orbital Hall current is stable under vortex correction.
But they choose a specific model for this order or something?
I think Gaussian disorder. That's
Yeah, so
standard.
maybe we need to do a computation with disorder to look at.
Yeah.
Right.
But disorder scattering is one very important issue that people started to consider just nowadays, actually.
Yeah,
Yeah.
I've not seen many papers doing that actually.
Yeah. But I think also maybe the symmetry is different compared to the 2D Rashba intrinsic spin-Hall case.
Yeah.
So I thought about it a really long time ago when I was working on this, but I came to a conclusion that in the presence of invariant symmetry, maybe disorder scattering is not so crucial as in the case of Rashba.
Yeah, I think the Rashba case is very peculiar because if you would add cubic Rashba, you wouldn't find, for example, this perfect cancellation of the effect and so on.
Yes, exactly.
So I don't see an obvious reason why this would be strongly suppressed.
Yeah. So generally, I think in realistic dispersion relation, I believe that intrinsic contribution survives.
Yeah.
But there will be a lot of change if there is disorder scatterings. That's
Right.
clear.
So there's not much work except for this paper, then this first paper that does actually this disorder scattering.
There are, as far as you know, there are 3 theoretical works. One by Ping Tang and Gary Bauer, and the second one by Liu and Dimitri Koser, and the third one also by Tatiana Bokut.
Right.
So there are 3 different groups working on extrinsic scattering problems.
Yes. Okay.
Yeah, that's the current status. Yeah. Thanks a lot for this. Is there more questions before I move on further?
Maybe just a clarification. So you said that this is not spin dynamics because it's not SU2.
Yeah.
What is it then?
So if I think about, for example, p orbital system, we have px and py, pz orbital degree of freedom. And if you count the number of degree of freedom that you have in this SU3 system, you can come to a conclusion that you need 9 different parameters to describe this system.
So it's SU3.
Yes. So you need 9 matrices to describe completely, like in semi-classical sense.
Okay.
So in that case, they are very similar to Gelman matrices that people.
Yeah, I know, because in your Hamiltonian, I just see the LX, Y, and Z, and then I thought, okay, this should be SU2, but there are other. Okay, thanks. Thanks for that.
Yeah, thank you. Okay, then I will go a bit further. So one lesson that we can have it here is that orbital Hall effect is really coming from orbital texture, which doesn't require spin-orbit interaction at all. So as I explained in the very beginning by introducing Condensed paper, you can understand orbital Hall effect as a parental effect to spin-Hall effect, in the sense that charge current can be converted into orbital current by orbital Hall effect, but then when there is spin-orbit interaction, then the spin current follows orbital current as a secondary process. And this depends on the correlation between L and S inside of a material. And this is a material-dependent property. And for the case of transition metals, for example, this is determined by the occupation of D shell. So mostly, in average, states on the left side of the D transition metals have negative correlation L and S. It means that they are anti-parallel. And then for elements on the right side, they have parallel configuration. So the trend is roughly correct, but not exact, because general intrinsic process is more complicated process than the LS correlation itself. So this is the result that I calculated from my ab initio code on real materials, 3D, 4D, and 5D elements. And to clarify, I calculate only the intrinsic contribution here. And so what you see first is that orbital Hall conductivity is really large, irrespective of the spin-orbit interaction strengths, all for 3D, 4D, and 5D elements. While spin-Hall effect is large mostly for these outliers, like tungsten or platinum, which are really widely used in spintronics for this reason, exactly. But in other elements, spin-Hall conductivity is much smaller. The maximum is like, let's say, 2000. But here, look at the scale. in ordinary materials like even vanadium and chromium, the magnitude is already 4,000 or 5,000. It's really huge. But in an extreme case, for example, in titanium, orbital Hall connectivity is really large, still a few thousand inverse on centimeter, but spin Hall effect in this case is almost vanishing, close to zero. So for this motivation and observation, we have designed an experiment to experimentally confirm orbital Hall effect in metallic titanium. So this work was largely carried by these two people, Young-Kwan Choi and Dae-Gun Jo, who are now in MPI CPS in Dresden at Uppsala University on experimentalists and theoretician each. The geometry of the experiments looks like this. So you apply current in the plane, and by in-plane current, you induce orbital Hall effect, and it means that it leads to accumulation of orbital states, Ly state, at top and bottom surfaces, respectively. But because light has certain finite penetration depths in metallic systems, usually about 10 nanometers. So that's why we can mostly detect orbital accumulation at the top surface. And the experimental data typically looks like this. So the Kerr angle, which is the change of the light polarization, is measured as a function of charge current density, and it's linear. Sorry, I didn't explain you the principle of the measurement. The principle of measurement is called magnetic optical Kerr effect, and you use linearly polarized light, and then when linearly polarized light interacts with magnetized surface, it's reflected, and the polarization changes. So the rotation angle, linear polarization angle changes, but also it slightly obtains ellipticity after the interaction. And they reflect both reactive and absorptive parts of the optical interactions. And that's how we extract the amount of magnetism at the surface. But the big question in this work was that when we measure this kind of signal, how do we know that this is coming from orbital Hall effect? Could it be from spin Hall effect by some, I don't know, exchanging mechanisms or something that we didn't consider before? Could be in principle. We cannot exclude all the possibilities. So therefore, we have carried out first principle calculation. But the main idea was that light interacts with orbital angular momentum really directly through dipolar interaction. And the way the light interacts with the spin is really through spin-orbital interaction. So in principle, when there's no spin-orbital interaction, light doesn't couple to the spin. And there is a term, but this term that couples directly to spin is really, really small, like 1,000 factors smaller. So the light mostly detects orbital angular momentum. So that's why actually at the end, we have shown that orbital angular momentum is about 100 times more susceptible to the light than the spin is. So for example, this is the first principle result that we have calculated for a given amount of orbital accumulation and for a given amount of spin accumulation, and calculated how much Kerr angle is induced for orbital and spin. And you can see here, the orbital signal is really strong. And note that spin signal is 50 times magnified because it's really too small value. So this made us to conclude that the measured signal is very likely to be orbital accumulation, not the spin accumulation. And of course, there are way more detailed analysis between the theory and experiment, but I hope this argument is already convincing enough for you. Okay, this was the case for central symmetric system, titanium crystal in FCC structure. But orbital Hall effect can also occur in non-central symmetric crystals. And one advantage of non-central symmetric crystal is that orbital angular momentum is not quenched. A very famous example is transition metal dichalcogen. This crystal doesn't have inverted center. So therefore, if you look at the band structure, this is famous for this belly feature in the band structure. And depending on the belly, orbital angular momentum is finite. And because of the broken inverted symmetry, orbital angular momentum at K and K prime values have different angular momentum values. It's already clear from the analysis for band structure, you see that the orbital character at K prime value and K values are different. And they're actually M equals plus minus 2 states each value. So there were lots of works in this direction, particularly by Tatiana Poport and Giovanni Pignale and Santika Bois. and many people. And what happens is that orbital angular momentum is already present in the ground state, depending on the value. But at the same time, Barry curvature is also value dependent. So what happens is that if you apply electric field, it drives anomalous velocity like this equals omega, and omega is value dependent, but at the same time, different values have different orbital angular momentum, so therefore you have valley Hall effect and orbital Hall effect, or some people call it now valley orbital Hall effect. So in my opinion, I think valley Hall effect is nothing but orbital Hall effect, and I think they cannot be distinguished because valley degree of freedom is locked to the orbital angular momentum also as well. So I think this is something that maybe the community of 2D materials can also learn from and maybe think further to look at the manifestation of orbital angular momentum in each valley in transport measurements. As far as I know, there are some smoking gun experiments, but not yet there's no convincing measurements on orbital Hall effect in 2D materials yet. So there are lots of opportunities that people can contribute here. And with a very similar idea, actually, we also carried out a project on 4F magnets. We considered a TMD-like structure of mixing europium and sulfur like this. And the idea was by using indirect exchange interaction between local moment of 4F orbital and I-channel electrons of 5D and 2P state. And then we wanted to harness this huge angular momentum of 4F orbital. And the idea actually really works, but it sensitively depends on the correlation. And actually we found that correlation is really essential to explain that the hybridations are really efficient for these valence states. And then when there is a hybridization between europium and sulfur atoms, and you can actually have very large orbital Hall effects because 4F states are coupled to moving states of p orbitals. So this was actually a really nice demonstration that we can even harvest these 4F orbital, which are usually localized, but by designing a material where p orbitals are overlapping with 4F orbitals. And when there is broken inverter symmetry, there's an effect called orbital-Rashba interaction. This is very similar to spin-Rashba interaction that many of you are familiar with, but this doesn't again require spin-orbit interaction. And this is an intrinsic coupling between the polarization related to orbital angular momentum in this manner. P is induced in the direction of L cross K. L cross K or L cross P, they all appear a lot actually in orbital physics actually. And then at the end, if you have effective E field along Z direction, for example, you have this type of coupling. So this induces momentum space angular momentum texture like this. So therefore, if you apply finite current in the system, you can shift the occupation function, and this can result in orbital accumulation. And orbital-Rashba interaction has been studied actually quite a lot more systems because this is ground state electron structural effect. So this study was largely carried by both emission and RPS community in particular. But nowadays also some papers started to appear in Orbitronics and spintronics community. Okay, so far I talked about then generation mechanisms. So till the end of my talk, I will explain you how orbital angular momentum is useful for spintronics. So MRAM magnetic memory, called magnetic random access memory, is not a joke. It's a real business, huge market potential. And in particular, this not only replaces traditional RAM that we use in computer, but this is quite crucial for in-memory computing by removing the bottleneck of transferring the information from the processor to the memory. So everything is calculated in the memory. It's called in-memory computing. And then MRAM can really significantly contribute in this direction. And one principle that we can use to control magnetization is by using spin current in this transfer geometry, by using spin Hall effect. But inspired from this, actually, we had a proposal that orbital angular momentum can also induce tilting of magnetization, basically exert torque. And we call this orbital torque. And in principle, this works, although it requires spin-orbit coupling in the parameter that I will explain you a bit later. And one nice advantage is that the efficiency can in fact be really high because orbital hole conductivity is really high in non-magnetic metal compared to the spin Hall effect. And moreover, we can now use a lot of actually environmental friendly materials for spintronic applications. So what I mean is that for having large spin current generation by spin Hall effect, heavy elements are unavoidable, like platinum or gold or bismuth, but they are really rare, as you can see here in this diagram, showing how abundant atom elements are in the atomic from the Earth's crust. But there are many room for these innocuous materials, including aluminum, magnesium, titanium, manganese, chromium, copper. So, and then orbital hole conductivities are really huge in those materials. Actually, this is one idea behind the EU project that started just recently called orbital electronics, and then we are trying to build spintronic devices out of orbital current. So this is one technological application. But physically, so what is happening? So in this case, there are 3 steps. The first step is that we generate orbital angular momentum by orbital Hall effect or orbital Edelshtein effect at interface. Orbital angular momentum can be injected across the interface, and then if there is spin-orbit coupling, then orbital angular momentum can exert torque. So spin-orbit coupling can actually act as a bottleneck because spin-orbit coupling is not so large in parameters. But at the same time, actually, generation mechanism is so efficient. So at the end, if you compensate very high efficiency on the first step and small efficiency in the third step, they kind of compensate at the end. It makes quite similar order of magnitude compared to the pinhole mechanism. So there are many things that you can study on each. Like on the first, you can study generation mechanisms. Not so many things are known except for orbital Hall effect and Edelshtein effect so far. And interface, I think orbital matching and transmission and transparency are very important issues, but not so much are currently really known. And a third part is also important, but I contribute a little bit, but to be honest, I think there are lots of things to be studied. So orbital torque, in my opinion, is a very complex phenomenon at the end. The reason is that there are many degree of freedom in a solid state which can carry and absorb and transfer angular momentum. But roughly, the mechanism can be classified into, in my opinion, 2 classes. The first thing, the mechanism is like spin transfer link. So the idea of spin transfer torque is that you really transfer the spin after the interaction. And if you look at the boundary condition, you see that the spin changes after the interaction with the magnetization. So the magnetization tilts also. In a similar manner, you can think of injecting spin into a magnet. But spin current can be prepared from orbital current by spin-orbit interaction, by converting orbital current into spin current by spin-orbit interaction. So at the end, the resulting torque will be given as the flux of the spin current. So at the end, the resulting behavior will be pretty much the same as a spin torque, almost identical. So this is not really surprising, in my opinion, but there is a unique mechanism that orbital angular momentum can contribute. But before I go further, there are demonstrations on how orbital angular momentum can be converted into spin current in 2020 and 2021 in these 2 works. So in this work, for example, in this experiment by Matthias Chloe, they have shown that this experiment can be nicely explained by assuming that orbital angular momentum is efficiently generated at the copper oxide interface, and when it reaches platinum layer, it couples to spin, and then there's a torque from insulating magnet. And this actually explains a huge peak here that is the case measured with copper oxide capping, but without copper oxide capping, actually it just shows ordinary spin Hall torque behavior, which is gradually increasing up to the spin diffusion length of platinum. And on the experiment on the right side, they have shown the switching experiment with and without platinum layer here, but chromium has different signs on the spin Hall effect, orbital Hall effect. So without platinum layer, spin Hall effect actually contributes to the torque dominantly. So it shows negative spin Hall angle at the end. But with platinum layer, positive orbital Hall current is converted to spin current in platinum layer, and it changes the switching polarity. This is a nice demonstration, I think. It also scales with the thickness of the chromium layer, demonstrating that this is really indeed coming from bulk chromium layer. So this is the demonstration, in my opinion, of the first type of orbital. So the second type is more, I think, intrinsic to the electron structure of ferromagnet. If you look at the theory of magnetic anisotropy, magnetic anisotropy is fundamentally caused by spin-orbit interaction, at least some part of it. So basically, you can look at contribution to magnetic anisotropy in this way by evaluating spin-orbit energy along the z-axis of particles. And you come to a conclusion that magnetic anisotropy energy is nothing but the orbital anisotropy along z-axis of particles. And this was nicely explained by previous XMCD studies, for example, and they have shown that the measured orbital anisotropy in in-plane, out-of-plane configurations measured by XMCD agrees well with magnetic anisotropy of thin film. But now, imagine that we inject orbital angular momentum from external source like orbital Hall effect. So, and this will then interact with magnetization through spin-orbit interaction. So, at the end, orbital accumulation together with spin-orbit coupling will induce effective field on M. And so therefore, the torque should have this type of form, spin-orbit constant times delta L. And this is fundamentally different from the spin torque. And this can be used really to distinguish from the spin torque, because nowadays people are really trying to clarify whether the measured torque is spin origin or orbital origin. And I think this is a nice way. For example, it's really sensitive to spin-orbit coupling of a ferromagnet, so crystal symmetry, and also momentum dependent orbital splittings, which we call orbital hotspots. But in principle, as I explained you, understanding the torque is really complicated business, because there are many degrees of freedom in solid state: electron degree, orbital spin degree, lattice degree, local magnetic moment. They all interact and exchange angular momentum. So I collaborated with Paul Haney in this sense, and we developed a continuity equation-based description of angular momentum transfer with orbital spin flux, orbital spin, and different channels of angular momentum transfer. And for the case of type 2 orbital torque, the essential term that contributes is this really S cross L term that describes the mutual exchange of angular momentum between spin and orbital angular momentum. But because of time, maybe I skip this slide on the first principle demonstration that this actually works. And there are many actually demonstrations on orbital torque now. So unfortunately, I cannot really track all the publications, but I try to summarize at least some of the audio works that I was able to follow. So there are roughly 3 directions of research. So first, people look at light element metal systems, which is seemingly like, because of small spin-orbit coupling, people assume that the spin generation is not sufficient here. So we can attribute the measured signal to orbital angular momentum rather than the spin. For example, surface copper is one example. But second idea here is to look at the competition between the spin Hall effect and orbital Hall effect, for example, and they can have different signs. So by carefully checking the sign of the signal of the measured torque, for example, you can actually tell whether the measured torque is spin origin or orbital origin. And the last part is I explained on the type 1 orbital torque that people can make use of this insertion layer like platinum to convert orbital current to spin current. So in fact, actually, in many experiments, they now try to check all those properties in one single sample, actually, to check the consistency. Because really confirming orbital signal is not really easy, because it really mixes a lot with spin signals. So this is one major challenge that we have in the community. So in the last slide here, I want to talk a little bit about ongoing unresolved issues. I don't intend to explain you what they are, how to solve them, but whether they are some issues there. So the one issue is that the community doesn't agree on the characteristic length and time scale. I also wrote a paper in this direction, showing that orbital angular momentum can go really far, but there are also theories showing that orbital relaxation length is really short. But there are experiments also. Most experiments show that orbital angular momentum seem to go quite far, actually, longer than the spin diffusion lengths. But I have to admit that we don't really agree on each other, and probably we don't really understand well.
How far? How many
Up to
numbers?
50 nanometers or sometimes 100. So this is really too far to be a spin relaxation length of, for example, tungsten. So in tungsten, for tungsten, it was measured in this communication physics paper, and also this Nature Nanotech paper in terahertz spectroscopy experiment. This experiment is particularly nice because they also measured how fast orbital current works and the lifetime of pulse. I think this is one advantage of ultra-fast spectroscopy here that people can contribute. And related to that is that we don't fully understand how orbital angular momentum can relax. There is one theory claiming that orbital angular momentum relaxes a bit like diagonal parallel type mechanism. And then, as far as I know, there is one paper which measured orbital Howland effect, and they extracted orbital relaxation scale. But comparing theory and experiments at this point is quite difficult. And disorder effect that Rembert raised before also, it's not so much well understood. So I know these 3 papers so far, but probably I might have missed them. But I tried to actually check thoroughly through Google Scholar yesterday, but I couldn't find further. So this also we don't really understand well. And optical generation is also quite relevant, especially in ultra-fast timescale, because they often make use of optical excitation in the beginning. And there are some theoretical works, especially by Peter Opnier, and also some from our team in English. And also related to block function geometry and topology. There are nice works actually by Tatiana Borgward and Marcia Costa relating the link between the orbital hole insulating phase with Howland topological insulating state. And I also have a work recently on the topology of chiral crystal. We show that actually topology is really driven by orbital angular momentum rather than spin-orbit interaction. And another aspect is that I probably briefly mentioned that orbital angular momentum can exist not only in atom but also by itinerant motion of electrons. And in principle, there is a Berry-based theory that you can capture all these contributions consistently. But there are still ongoing process from many different groups. And I'm also working in this direction quite seriously nowadays. And finally, I think reciprocity is also one very controversial issue. That there are some claims showing that the reciprocity is violated in the case of orbital transport. And I think probably this is related to very unconventional transient nature of orbital angular momentum, in the sense that orbital angular momentum appears and disappears at the same time. So in this sense, we have to strictly define what is the coordinate and what is the force, what are really measured in experiments. So without setting the ground, I think it's really hard to clarify. So still ongoing process. But yeah, this is I think the current situation. We are only looking at the tip of an iceberg here, and there are really lots of things that we still have to clarify further. So I hope in this talk I didn't give a wrong impression that a lot of works have been done here, but there are way more works to be done. So that's one message, especially in many other materials. I mostly focus on transition metals, but there are other novel materials. To me, novel materials are actually basically non-metallic compounds, like 2D topological insulators, frustrated magnet oxides. There are many things that you can explore. Please do. because now community, I think, focus a lot on tracer metals. I think these novel materials are, in my opinion, very good because, in a sense, electronic structure is sort of an extreme case. So having extreme case is good for physics theory because you can really compare theory experiment in a peculiar case. So this is one philosophy that I have for novel materials. Yeah, and before I close, I think I really have to thank everyone who inspired me and who helped me and work together over many years to the journey, and also all the funding sources from Spin Plus X, Top Team Project from Mainz, and Orbital Electronics from the EU, and also Computing Center as well. And in particular, I'd like to thank my post supervisor, Yuri Mokosov, and my former colleague, David Joe, who is now in Uppsala, my thesis supervisor, Henry Lee, and also many other experimentalists who really opened their experimental data from early stage that was really unexplainable at that point, and I couldn't explain. But over time, I think somehow pieces are fitting together slowly, hopefully, and I think we will make much better. So yeah, this is the summary of my talk, graphical summary, and yeah, thank you very much for your attention, and yeah, I'll be happy to answer your questions later.
Thank you very much, Dongwook, for this excellent pedagogical presentation. Are there questions? Let's take a few minutes. We're a bit over time. Let's say max 5 minutes or so.
Yeah.
Ali.
So thank you for your presentation. So I have a question. Let's consider that we apply the electric field and we have the orbital and non-equilibrium.
Yeah.
And let's turn off the electric field.
Yeah.
So it's gonna feel, it's gonna relax that one.
Yes.
So if we don't have any spin or the coupling, then it relaxes and we have a distortion to the band structure of the system. There's somehow like the tension or temperature, or even that it could, excite, somehow just having interaction, hyperfine interaction with the units.
I see. That's a very good question. So let's first say, let's assume that there is zero temperature. And then when the lattice is frozen, what will happen is that there will be coupled oscillation between angular momentum and quadrupole moment, as I explained you. So there will be oscillation. But in finite temperature, then orbital angular momentum can couple to phonon because it couples to lattice degree of freedom very strongly. So eventually, once it goes to phonon, I think the chance of coming back to electron system is quite low. So we can consider it as relaxed. So I think that's likely to happen. So I think
there could be a distortion of the crystals. It's really big then.
Yes, in principle, yes. In principle, orbital angular momentum is actually a key link to understand Einstein's Hasse effect. So there's, say, spin degree of freedom, but there has to be orbital degree of freedom to couple to the lattice. So there can be distortion of or rotation of the rigid body eventually if you have finite angular momentum, if you switch off suddenly. Yes. Fundamentally, but I don't know how large the effect is be, but fundamentally, I think this is what is going to happen. Yeah, thank you.
More questions?
Yeah, you can always write me an email if you have further.
Oh,
Yeah.
You mentioned it just verbally, but all your pictures are using some kind of isotropic texture for the
Yes.
white orbitals.
Yeah.
And then you get a nice separation between the tangential and radial kind of features. In a real band structure, what actually happens? To imagine you have a Fermi surface that is not at all spherical.
Yeah.
Is there some rule for the preferred orientation of the orbital with respect to Fermi surface itself, or the k direction? Because the absolute k direction is useless then.
Yeah,
because you have pockets all over
yeah.
the place.
Yeah, totally. So in this case, of course, if we look at k points close to high symmetry points, there are certain symmetries because symmetry is high, but in arbitrary k direction, there's no strict rule because all lowest order and higher order hoppings will enter there. So it depends on the system to system. I think. In general, there will be working effect as well, and then orbital character will change, not in a very intuitive way, I think, but at least what governs here is the symmetry, for example, if you have embodied symmetry, and then in this case, then you can know that particular certain types of orbital textures cannot be allowed. That's how much we know. But details of how texture will look like will be material-dependent properties.
So the variation of the texture determines the amplitude of your orbital Hall effect, how much it's actually
Yes.
makes the change.
Yes, that is really important because
That's what you want to maximize and how you want to.
exactly. Yeah, this is what is related to the gauge transformation U that I showed in the very beginning of my talk. So the more rapid U changes in K space, then the bigger the Valley phase related effects are generally. So this is one of the directions that people are thinking to increase the magnitude of the orbital Hall effect or orbital related Valley phase effects. Yeah, thanks a lot for good question.
I was also wondering about the distinction between your type 1 and type 2 orbital work injection.
Yeah.
Can you really distinguish the two and determine how much accumulation you really have and how much is being transferred directly through some spin orbit coupling? You also have like a spin orbit coupling at the interface, or crystal house, whatever.
Yeah.
That even if your metals are all light, can still inject some stuff.
Yeah. First of all, experimentally, I don't have a good idea. I think they have to, experimentally have to try harder. But theoretically, I can separate clearly. So one thing that I didn't show you is how this continuity equation approach applies in a real material system. So this is one example that I calculated for chromium cobalt iron bilayer. And these three terms show that this is spin flux, and this is the spin orbital torque, S cross L torque, and this is torque acting on the magnet. So I can really resolve layer by layer, and then we can assign this spin torque, the spin flux term, as the sum of spin injection plus converted spin current from orbital current. At least we know this much. So by looking at when this conversion takes place and where and how between which degrees freedoms angular momentum is transferred, you can understand in detail actually how angular momentum transfer occurs, at least theoretically.
Okay, I think we should stop here because I think my chair is thinking of another question in the 5 minutes.
Yeah, I think yes.
So thank Dongwook again. Thank you very much.